example, which is this, which I hate writing stuff, like, I don't know, I mean, just, I hate that. I want the air, I like the squiggles, like, I don't know. It does make it easier to keep track of when we do this, if we know for sure that OET, we're never gonna deal with, like, mess with any of the stuff connected to this. The only thing we're gonna mess with is, like, the oxygen and whether it's got something bound to it or a negative charge, right? If we know for sure that that's the case, yeah, this can definitely simplify the shapes you're looking at to help you count carbons and keep track of everything and, you know, make drawing mechanisms easier. But they give you this example, and now they're trying to do the mechanism with this one. For I don't know what reason, I mean, whatever, let's just do that. Yeah? Better? I like this. All right, so we've got I don't want to put that there. I'm going to put that, the one that we don't use, just going to go up here. Because it's nice to remember there too if we're going to draw one. All right, so we've got this. And let's see. We've got, yeah, and we've got ETO minus. Because lone pairs are good. They help us remember where things are. And this guy, oh, mechanism color. This guy, you know, hey, that's a really nice hydrogen, but it's definitely somewhat acidic, so we can do this, and we can point it to there and do a nice little that, which of course has a nice little resonance structure of this is why we draw arrows before we just start drawing structures. It has a nice little resonance structure. It is much more convenient to draw like this, which gives us this, that. And this still has, well, okay, I'll draw the hydrogen down now, but that's just because that, with a double bond, that's gonna really dumb up there. So, fine, I'll do that now. So we've got this going on. And this is in equilibrium. In the end, we get ETOH, right, as well. And this pKa is around 15, right? What's the pKa of the alpha, the protons on the carbon alpha to a carbonyl? I have your pKa table in a slide somewhere.
Is it similar to alcohol?
Well, it's not exactly the same as the alcohol. Wait, that's not where I was trying to go. If I go to your lecture slides, I know I have it on chapter 18. I just want to make sure that this is on your, like, I have the pKa of it over here, but, oh. Just trying to do a double screen, but there are two screens here. pKa table, copy, paste. There we go. There we go. All right. So we have, let's see. Well, it's not a diketone, because then we'd be real acidic, right? That'd be a pK of 9. That's real super acidic. But, like, of course it is. It's not just alpha. It's double alpha, right? It's alpha to 2 different carbonyls. We've got, here we go. Okay, so esters and ketones are slightly different. And that's because the esters are going to be a little bit more difficult to deprotonate. Oh, can you guys see that? Sorry. So, primary alcohols, right around 16, 15, that area. Tertiary alcohols, all right, they're a little bit higher, but not by a ton. Ketones, they're 18 to 21, and then esters, they're 25. So they're a little bit higher. Part of the reason for that is, have you guys talked about electron withdrawing and electron donating groups a little bit yet? Or did you do that in OChem 1 at all? Okay, that's cool. It's generally an aromatic, like benzene thing, so we will talk about that. But let's start with a tiny little aside about it. So electron withdrawing is just when we've got
Wait, if the pK is 25, is it 15?
that one's 15, and this pKa is around 25. So, yeah, which side of this equilibrium is going to be favored? We have, over here, going forward, we've got an acid with pKa 25 acting as an acid. But going backward, we've got an acid with pKa 15 acting as an acid. Which one wants to act like an acid more? pKa 15 or pKa 25? 15, right? So actually, this kind of looks like this. Weird. But it's acidic enough that, like, as long as there's enough going on to hit an equilibrium, to have, like, stuff going on, we make a little bit of this. Once we start using this in a reaction, a little bit more gets made. And then we use that in the next step, and a little bit more gets made. So this is that weird thing about where we can kind of, what we need to happen, what happens with the reaction isn't what's favored in this step, but as long as it happens a little bit, as long as it exists in equilibrium, once we use up that product, we're just gonna keep making a tiny bit more, right? Is that okay? Okay, yes.
I'm just a little still confused on, because that ester enolate up there
Yes.
says 25. How is that different from the one on the right that you're showing us?
Yeah, this is the same.
No, the one on like the right, like the.
Oh, this pKa goes to this. Sorry.
Oh.
Yeah,
okay.
I'm so sorry. I
No,
was
you're good.
putting the pKa next to the acids because I don't like pKa sitting next to the bases,
Yeah.
and I get that these are like right next to the bases, but the pKa is, well, acids have pKa's, right? And yeah, acids have pKa's. Bases, well, they can have a pKa if you make them look like an acid, but if you make them act like an acid, it has nothing to do with the pKa of its conjugate acid. It's just a whole new thing happening, right? Except that you know it's going to be a way bigger number because you already stole one proton, so it's probably going to be harder to take another one. So this step of the reaction is not overly favored, but it totally still happens, so okay. I mean, as long as we are as long as we're in resonance, as long as we make some of that, then okay, cool. I guess we make some of that. So let's just redraw this. Yeah. Yeah, let's redraw our enolate, and let's do I would rather use red to draw things than green, because green is a little harder to see, but I really don't want to suddenly use the color that I have coded as nucleophile to draw the electrophile all of a sudden. I'm going to redraw this real quick. Sorry. We've got this, of this, and some part of this is going to act as the electrophile, namely this carbon using these electrons. And then we've got another mole of the same ester. You know what? This guy is not going to do any enolate things. So for now, let's not worry about that. Yeah? All right. So now we've got this. And, well, this guy we get to use as, this guy's doing enolate things. So we know that's the nucleophile, right? And the source of electrons is going to be this carbon-carbon double bond because we'd much rather stick with carbon-oxygen double bond in the end, way more stable. And this carbon is going to be the carbon that we're going to form a bond to when we use these electrons because, well, this guy doesn't have anybody to, like, placate him if this carbon takes the electrons, right? But if this carbon takes the electrons, this guy goes, hey, let's both be happy. So we attach to that one. Over here, we don't have any of that enolate stuff going on, so we can just do our nice normal carbonyl-carbon is our electrophile thing. So we are going to do a nucleophilic attack. And this is only catalyzed by base, so we don't have to worry about anything else. But also, if it were catalyzed by acid, we would do our nucleophilic attack first, and then do a correction afterwards. Do the first step after the second if we needed to. So this guy comes around and attacks there. This goes, hey, carbon, chill out, it's fine, you're good. And this one goes, oh, it's fine, I'll just take these, because otherwise you're not going to have that, right? And we end up with not a ton of room on board. So this, we're going to do there. Perfect. Gorgeous. That makes sense. And let's start out by drawing. Oh God, okay. This is the part where, like, you start building things in your head, and you know, it's a little different to keep track of all the carbons and like do the actual thinking while you're also performing, essentially. Like, it is different than in a test situation. So I'm going to use my cheat sheet, make sure that I do this properly. Okay, so, all right, so they draw this, fair enough. I did start actually drawing the carbonyl carbons, didn't I, at one point, because that helps us keep track of things. Would it be more confusing or less confusing if I leave those guys without the carbons explicitly drawn, and then the next time I draw it, I have carbons explicitly C? I think it'll be, that sounds a little I
think it matters.
Give me a yes, I'll be confused, or a no, that's probably fine. Okay, cool. I was trying to figure out, I didn't define them both, so I was like, no, don't do that, or no, that's fine. All right, we're gonna draw it like this, because, so we're gonna take this carbon, and this carbon now has, it forms that, right? It's got, oh wait, okay, that's the one that's gonna have to be over here. I drew the one that we had already played with first, but this has to be over here because these make a bond that way, and that's the direction we've drawn them. Fine. All right. This carbon is green. It has one bond to its negatively charged oxygen, and then it's got that, and it's got that, and it's got its new bond to this carbon. This carbon is attached to that, right? Because we just reformed that double bond. It's attached to this as well, because we already had that. And this isn't the carbon that does things anyway, right? So we go to this carbon, nucleophilic carbon, and the nucleophilic carbon already had a bond to an H and an R. Wait. Yeah, yep. Thanks. It's like, wait a minute. God. This is why I should draw things in the order that I'm going to draw them, or whatever. Visually, I don't know. It's probably a good thing that I didn't teach you spectra because, or spectroscopy interpretation, because that would, I don't know how well that would have gone because I don't know any of the numbers. Like I know whereabouts to look because I always set the axis, like for IR, 400 to 4,000, always set it at that, and then I just have to know, you know, about yay here, about yay far. That's how I do it. Okay, this is our carbonyl carbon. We have an R, we have an H, and we have, that's our new bond, and then we have a bond to our carbonyl carbon. There, this guy. And now I'm not going crazy anymore. I mean, I was never going crazy. I was just giving you guys the opportunity to practice spotting mistakes so that you can put that into practice in your own homework and exam situations. So you're really good at knowing what kind of mistakes to look for, and then you get to correct them before I get to them. Yep, that's on purpose. All right, so we have this. This is our tetrahedral carbonyl addition intermediate, right? It's just whenever we add something to a carbonyl, we get this tetrahedral carbon, and we know that's an intermediate because we've got a CO and a CO. So we've got two CO single bonds. One of them's probably gonna go, right? And let's see. So that's gonna be the next thing that happens. This guy goes, hey, you know what? It's been nice having you here, but it's just, everybody's happier if we do this. That looks like a weird-ass arrow, so that's gonna be a nice, there we go. Now it's not like weirdly curved. All right, that does this, and we get and all this red stuff over here, nothing has changed. Yes?
So we don't, like, what's the point of the H2O, HCl, like the acid workup?
Oh, we are not.
So,
We're gonna get there.
Okay.
There are two more steps because yeah, it does look like we just formed our product, right?
yeah.
This is the end product. I just didn't notice because it's 3 of 5 steps. So we just formed our product. That's it. But let's go back and look at things because, well, the pKa of this is 10.7, which, I mean, you could have just called it 9 because up there we've got a, we don't have this exact example, but we do have a 1,3-diketone at pH 9. So that's fine. That could be an all right enough estimate. And then we have that sitting in solution with OET minus. And these guys can do an acid base where we get HOET and we get and this guy can go, hey, what if I took that? And this can go either this way or this way. I don't know that it really matters. So we're gonna do this one for funsies. This guy keeps that. My alarm's about to go off because class is almost over. This guy still has its R that I'm gonna draw down here now just because we've got a double bond there. Okay, so that's a pKa of about 10.7. This is a pKa of about 15. Now, which one's better at being the acid? Our product or stack? All right, you guys have labs, so we're gonna do this like hella fast. You can pack up and stuff, but like, which one's gonna be favorite, or which one is better at acting like an acid? The alcohol, pKa 15, or the stuff we just made? Stuff we just made. So basically, this happens and we get mostly this. So that's why we need a water workup. It's literally just, we made this whole thing in basic solution, or a basic environment, and now let's just go ahead and like protonate all of the random deprotonated alcohols, and that will let this go back to here. So we, I guess on this is technically on that side of it. So we're gonna get rid of all this, push equilibrium that way, because this is the only thing we're gonna have, and then we'll actually form our desired product instead of, it's basically there, it's just sort of deprotonated. Yeah?